So let's plug some numbers in here. Let's... So I'm just making something up. Our lever arm has an X component and a Y component, so it's pointing up that way. Our force has an X component and a negative Z component, so it's pointing back that way. This force, as long as it has a component perpendicular to the lever arm, this force will produce a torque. Okay? Now, when they're written in vector notation like this, having an R that way and a force that way, it's going to be a bit challenging to try to figure out the angle between them in order to find the perpendicular component. If you really want to try to find the perpendicular component, that's fine. But I'm lazy. The cross product does the same thing for me. It makes it really easy. So the cross product, all I need to do is set up a matrix. Remember, you always put the R values in first. So 4 meters is the X component, 3 meters is the Y component, 0 is the K component. It's important to put the 0 in. The force, 6 newtons is the X component, 0 is the Y component, negative 5 newtons is the K component. So you do need to put the zeros for any components that you don't have. That's important to put in there. So I hat. If we cross out the row and the column that have I hat in it, we're left with these 4 numbers. Starting with the top left one, we multiply it by its diagonal. So 3 times 5, negative 5, is negative 15 Newton meters. Minus the other diagonal, but the other diagonal is 0 times 0, so 0. So there's our X component of our torque. Y component's negative. Cross out the row and the column that have the J hat in it. That leaves us with 4 numbers. Starting with the top left, we get 4 meters times negative 5 newtons, so that's negative 20 Newton meters. The other diagonal, we have 6 times 0, so minus 0. The K hat, we need to cross out the row and the column that have the K in it. Start with the top left-hand corner, 4 times 0 is 0. Minus the other diagonals, so minus 18 Newton meters. So this means our torque vector is negative 15 Newton meters I hat. Negative times a negative is a positive, so plus 20 Newton meters J hat. Minus 18 Newton meters K hat. By the way, I never mentioned too, the units on torque, newtons times meters, we don't call that a joule. Remember when we did work was force times distance, we ended up with newtons times meters there too. We called it a joule then. We don't call it a joule here. We just leave it as newtons times meters. So this vector, we have a negative X component, a positive Y component, and a negative Z component. So that means this is your rotation axis right here. My arm would be the rotation axis. If you put your thumb in that direction, your fingers show you which way around your thumb that the object would rotate. Okay. So your object would be spinning like this.
How'd you get the negative 18 Newton meters again?
Because we crossed out the column and the row that had K in it. 4 times 0 is 0, and then minus the other diagonal.
Minus the diagonal.
Yeah.
So this
same rule applies here. We can find the magnitude of the torque vector, right?
Certainly. Magnitude, you can use Pythagorean theorem. Pythagorean theorem works three-dimensionally. So the square root of a squared plus b squared plus c squared. Certainly. That'll give you the magnitude of the torque. So the cross product multiplies perpendicular components together. Notice, well, it's kind of hard to tell here. The result of the cross product, the torque vector, by the way, is always perpendicular to these two. Your result of the cross product is always perpendicular to the two vectors you crossed. Okay. Let's show you. Let's put our R and our force both in the xy plane. So we'll leave R the way it is. I'll just take off the z component of the force. So our lever-arm vector still has an x and a y component, but now our force only has an x component. In this case, it would be really easy to find the perpendicular components. Force is along the x-axis, the lever-arm's up here. Which piece is perpendicular to the force? Which one of these is perpendicular to this? Just the J. So our torque should simply be 18 Newton meters. Let's do it this way. I'm just putting a zero in for the z component. So I hat, when you cross out the row and column that have the I hat components in, starting top left, 3 times 0 is 0, minus 0 times 0 is 0. So we get 0 for I. J, cross out the row and column, 4 times 0 is 0, minus 6 times 0, which is 0. So we get 0 for J. K hat, cross out the row and the column, 4 times 0 is 0, minus 6 times 3. So our torque would simply be negative 18 Newton meters K hat. Multiplying the 6 times the 3, just because you're multiplying perpendicular components, will give you the magnitude, but it doesn't give you the direction. So you need to figure out the direction on your own. If you do the cross product, it gives you the direction. This torque is specifically in the negative K hat direction. That's into the board. Into the board means your object's going to rotate clockwise from your perspective around that axis. Okay. So the torque vector is always perpendicular. Z is perpendicular to both x and y. The torque vector, the resultant of your cross product, is always perpendicular to the two vectors that you crossed in the first place. This same process works for angular momentum for the point mass. If you're using angular momentum as R cross P, you put the R values in the middle and the momentum values on the bottom, and you do the same thing. It's the same process. Okay. So there was two ways to multiply vectors together. One was the dot product, which is what we did when we did work. The dot product multiplied parallel components, and you came up with a scalar answer. There was no direction associated with it anymore. The cross product, you multiply perpendicular components, and your answer is a vector. So two different ways. Okay.